So next speaker is Soheil Bakhtiari.
Yeah.
You're being nice. Who's going to be speaking to us about temporal multi-hazard risk assessment. So we have a risk assessment team going on today. Of interconnected infrastructure systems using dynamic Bayesian networks. I'm curious what makes them dynamic. Soheil is supervised by Dr. Reza Najafi, Dr. Katsuichiro Goda, and Dr. Fasantia Fasani. That's a lot of advisors. I hope they're nice to you. Well, with that, Lord, yours, please.
Yeah, thank you.
Yeah. The leader is that one. And then if you go left, right, you have to point here. Yeah, you can do that too.
Okay, hello everyone. Today I wanted to do the brief presentation of the recent work that I did under the supervision of Dr. Najafi and Dr. Pirosini from Civil and Environmental Engineering Department and Dr. Goda from Earth Science Department. So I wanted to actually give you some examples as background or as introduction for my presentation, and then go for research objective for this work and the brief discussion on the study area and methodology that I used for this work, and then some of the results and discussion related to those results. And at the end, I will finish my presentation by key findings. So as an example, Hurricane Sandy occurred in October 2012, and the most affected area was Caribbean Sea to the northeastern coast of the USA. The consequences of that event was more than 100 billion US dollar loss and more than 20 fatalities. Besides road closures, power outages, subway interruptions, and telecommunication failure and damages to petroleum and electricity infrastructures. My research mainly focuses on the infrastructure or interconnected infrastructure systems. Another example is tropical storm Matthew occurred in September 2016, again in Caribbean Sea to eastern seaboard of the US. And the consequences is damages to telecommunications, roads, water supply, healthcare facilities, and power distribution that affect the other entities or assets in that area. Hurricane Dorian, September 2019, in Canada, Nova Scotia, Newfoundland, and New Brunswick, affected by that event. And failure in electrical grid led to power outage for more than 400,000 people, and telecommunication failure, road closure. So the critical infrastructure is crucial for all communities, and basically any disruption, no matter small or not, can result in performance of those infrastructures. I chose this picture to show how one failure in one of the entities can propagate through the system, interconnected system, like as domino effect or cascading effect that we can use this term in this matter. Basically, based on the exposure of critical infrastructures to natural hazard around the world, many countries deals with this actually effect of these events on the critical infrastructures. So the objectives of this work is how to use or to develop a novel risk assessment framework to address dynamic effect of the natural hazard or any hazard on interconnected systems. So we utilize the dynamic Bayesian network to do the multi-hazard risk assessment under the infrastructures. The study area that we chose basically is Saint Lucia, a volcanic island in Caribbean Sea. And we only focus on the southern part of the Saint Lucia. There is a very important international airport on that. And the data that we have related to the interconnected complex system includes actually 109 entities including assets and components located in that area. Actually, what happened in that event, I mean, the tropical storm Matthew event in 2016, affected entities, fire and rescue building, runway status and taxiway apron status located in the international airport and the southern part of the area. And this figure shows the affected nodes on the top, runway, taxiway, and fire and rescue building affected by those two flooding nodes to be added to the 109 nodes. I just chose some of the nodes affected by those target nodes at the top, and the other nodes are mainly focused on airport normal operation to show the status of the airport in that event, and tourism affected by the disruption of those three nodes and propagate of the disruption of those three nodes through the network. It shows the Bayesian network model to model the connected network that each node can represent one of the assets or components located in that area, and each edge shows the interconnection or dependency between the nodes. The aim of this research was going beyond the static assessment of the risk. So we decided to use these actually to follow this event, like having disruption during the event or after the event, and having restoration after the event. So we move forward to dynamic Bayesian network, which is the extension of Bayesian network, in which each Bayesian network or each slice is the Bayesian network, which is connected to the previous state of itself, and each node can connect it to the previous state of itself. It's actually, each node can connect it to the parent of itself in the actually same time slice, can be connected to the previous state of itself, and can be connected to the previous state of its parent node. So we simulated the disruption. This figure shows two slices of the disruptions. So we have these three target nodes and the two actually flooding nodes affect these three nodes. I didn't show the other 106 nodes to this figure, in this figure. So T0 and T1 shows two slices of the disruption behavior of the system, and these two slices shows the restoration time. Like we don't have any flooding node in this figure, and we have 13 different slices for restorations. We have 9 actually time slices for disruption and 13 time slices for the restoration based on the data that we have. Based on the time of the flooding, I didn't show these data here, but we have some data related to the flooding, the duration of the flooding and duration of the restoration based on the data that we could find from the news report. So this figure shows the disruption and restoration of the target entities, the 3 entities affected by the flooding. And because of the only try to focus on the airport normal operation to show the status of the airport and tourism. So this figure shows the disruption and restoration of the airport and the tourism based on the disruption and restoration of those 3 target nodes. So we decided to use 7 different scenarios. The first one shows a scenario that all 3 target nodes fails. 3 scenarios shows just 2 of 3 target nodes fails. And the last 3 scenarios shows just 1 of one of these three target nodes fails. Basically, because we wanted to show that how any mitigation method that can actually prevent any of these target nodes can affect the disruption and restoration of operation of the airport or disruption and restoration of the tourism. Based on that, this figure shows the disruption and restoration of operation of the airport and tourism based on these 7 different scenarios that we try to simulate. And this figure shows how long does it take for each airport normal operational tourism nodes to actually get again the working probability of 90% after the restoration. We try to find, for example, as an example, that's, for example, how long does it take to get the 90% of the probability of working after the restoration in this figure. One of the other actually objectives that we tried to address in this study was how to simulate multi-hazards, having more than one hazard in the event. So unfortunately, we didn't have enough data for the other hazard, but we could find some news and report that showed there were some landslides that made road closures in that area for actually corresponding to that event. So we tried to simulate multi-hazard, adding landslide that cause disruption in transportation system. So just simulated that we have disruption for intercity road transportation, one of the entities included in the 109 nodes that are introduced. So we just assume that we have disruption in intercity road transportation because we had some reports that mentioned there are some of the roads were closed basically based on the landslides. And we assume that after the event, we have some portion of restoration for that case, basically based on actually data that we could find on the news. This figure shows disruption and restoration of the target nodes. So to show the disruption and restoration for the tourism, we can see that in the last scenario that we chose, the tourism affected by the disruption of the intercity road transportation. And this figure shows the time that it takes for them getting 90% of the restoration for tourism and airport for related to these multi-hazard section. So based on this approach, we try to find the resilience resilience index corresponding to those two nodes based on different scenarios. And as a conclude, we find that dynamic Bayesian network is a good approach to choose multi-hazard resilience assessment to come up with multi-hazard resilience assessment for the complex system. And we could find that airport normal operation or operation of the airport and the tourism are two vulnerable entities located in this area. And actually, we need to have a robust framework to assess the risk, and we could consider direct and indirect dependencies in any interconnected systems to assess the risk. And at the end, for the future actual studies, we can consider wide range of hazard or different resilience metrics, and having more accurate data can actually move the develop framework to have a comprehensive risk and resilience assessment. Thank you for your attention.
Thank you. Questions for Soheil? We have only time for a quick one. Yeah.
You mentioned data a couple of times. Was it the lack of data because of the location of the study?
Actually, at first, we tried to find data related to the interconnected infrastructure system in Canada, but I couldn't find anything because the problem is of the infrastructures and interconnected infrastructure to get the data from different stakeholders. But the study area that we chose was the study area that Dr. Najafi did another approach of risk assessment with one of his students before. However, they use another commercial system to come up with the risk assessment. We add some assumptions, we add some calculation to come up with probabilities assigned to each entity. And based on that, we could actually use this data to check the framework works or not.
Thank you very much.
Thank you.
Yeah. If you're okay. You're okay. Okay. Cool. So third speaker of the day is Elshaimaa.
Yeah.
Ahmed. So laser is this one. Yeah. Who's supervised by Professor Ashraf Al-Damati. And today she'll be speaking to us about the effect of roof curvature on the rigidity and stability of cable domes. With that, the floor is yours.
Hello, everyone. Before I start my presentation, I have a question for you. Which one do you think is more rigid than the stuff? The curved chip or the flat one? Those who choose the first one, please raise your hand. Okay, and those who choose the second one, please raise your hand. Okay, we will figure out if this is the correct answer by the end of this presentation. In my presentation, I'll talk about the introduction of this research, the objective methodology, results and discussion, and finally the conclusion. Cable dooms. Cable dooms are one of the most widely used types of cable structure because of their lightweight, aesthetic view, and adaptable forms. And it can be used for covering large areas such as arenas and stadiums, and it consists of cables and struts, self-balanced by a proper state of self-stress with marginal beam. The first established form of cable dome was with positive Gaussian curvature was the Geiger dome in Seoul, while the largest one was the Georgia dome in Atlanta. The biggest challenge in designing cable dome is the potential instability under excessive loading due to slacking cables or buckling in struts. And this motivated designers to develop new forms with better stability and rigidity. As you can see here in the first picture, this is the traditional one with positive curvature. Two new forms with zero and negative Gaussian curvature was developed recently. The first one developed by moving a positive curve over a straight line, while the second one developed by moving a positive curve over a negative curve. Those new forms are intended to have better stability and rigidity than the positive Gaussian curvature, because of the double curvature of the roof. Actually, the positive one has the bearing function, while the negative one has a stabilizing function. But this should be thoroughly investigated before using it in practical application. In this regard, my research aims, or this research, actually part of my research, aims at investigating and comparing the rigidity and stability of those two new forms to that of the traditional positive Gaussian curvature, and also studying the effect of rise and sag values on the rigidity and stability. To do this, we employ the arc length method by incrementally increasing the external load from 0 to 10 kilonewton. And the rigidity is assessed based on the maximum deformation, while stability is assessed based on the buckling in struts and the slacking in cables. And all case studies will be designed and optimized to the minimum weight at L over 500 displacement for a fair comparison. The known and unknown parameters for the case studies are as follows. As you can see here in this picture, all dooms have the same plan dimension, X and Y coordinates, and also the same length of struts. As you can see here, the struts, all of the cases have the same length of struts. While along X direction, all of them have the same rise 10 meter, and along X direction, the positive one has rise 10 meter, while 0 is a straight line, and the negative one has sag for the negative curve, 4 and 8 meter, to investigate the effect of changing the sag on the rigidity and stability. So a total of 4 dooms are considered in this study. The unknown parameters are as follows. The first category is the vertical coordinates of all nodes and the pre-stress distribution in cables and struts, usually defined through a process called form finding. Second, the cross-sectional area and the magnifier of this pre-stress by a factor gamma, and those are optimized to the minimum weight through an optimization algorithm. For the first step, which is the form finding, we develop a real-coded genetic algorithm that represents the surface with 2 nervous curves. The first along x-axis with 4 control points and a negative curvature, and the second along y-axis with 4 control points and positive curvature. The control points are the variables of the algorithm, and each candidate generated by the genetic algorithm develop a nervous surface, and then the doom is projected on that nervous surface. And using the SVD technique, we can calculate the pre-stress. Then it checks the constraints, which is tension in cable and compression in struts. After this, we calculate the equilibrium error of this pre-stress at all nodes. It should be summation x, y, z equals 0. And the aim of this algorithm is to find a nervous curve with minimal equilibrium error at all nodes to be less than 10 at -7. So this is the first step. The second step after getting the feasible form is to optimize the cross-section and the level of that pre-stress. It's usually one number denoted by gamma, and the procedure is to assume initial value for the pre-stress. For example, 40 meganewton. And through the sub-iteration, we design the doom to the minimum weight and get the weight and displacement corresponding to the 40 meganewton. And by increasing the level of pre-stress incrementally, the total displacement decreases till it reach L over 500 and the iteration stops. This is our target displacement for all dooms. After optimizing the doom, we applied the arc length method by incrementally increasing the external load from 0 to 10 kilonewton and monitor the stresses in cables, the black line, and in struts, the blue lines. And as you can see here, for the positive cable doom, the traditional one, slack occurred at load multiplier 2 in all cables around this ring B. And at load multiplier 8.5, buckling occurred in all struts. And this indicates failure of this traditional load under excessive loading. While 0 curvature doom, no slack happened in the cables. However, the buckling occurred at load multiplier 6 due to the rotation of those upper nodes causing rigid body buckling of the struts. Okay. For the negative one with 4 meters, we didn't see any slack in cables, and the buckling occurred at load multiplier 9 0.5, which is very good, and only happened at the outermost struts along this stabilizing curve. So the negative curvature show more stability than the positive and 0. Increasing the sag to 8 meters decreased the stability a little bit to for the buckling to occur at the load multiplier 6 in 4 struts. For the rigidity, we monitored the maximum displacement with the load multiplier for the 4 cases. As you can see here, the yellow one, the positive curvature dome, the traditional one, the rigidity started to decrease drastically at load multiplier 2 due to the slacking cables and buckling in all struts. While 0 curvature dome, the dark blue, experienced buckling at load multiplier 6 and started to decrease the rigidity. While the negative curvature dome sag 4 and 8 meter actually showed great rigidity with increasing loading, and thus conclude that the negative curvature dome has more rigidity than the 0 and positive curvature cable domes. Sum up, negative Gaussian curvature cable dome has more rigidity and stability than the traditional positive curvature and also than 0 Gaussian curvature cable dome. And the stability decreases a little or slightly with increasing loading. While the 0 curvature dome loses its stability due to the rigid body buckling of struts. Positive Gaussian curvature dome is the worst form because it loses its stability and rigidity under excessive loading due to slack in cables and buckling in all struts. And back to the question in the beginning, I think you figured out that you had the correct answer, that the double curved surface is more stiff and rigid than the flat one. Thank you.
Questions from the audience?
I'm not familiar with domes, so you are the expert. If positive or the traditional domes are more, you can say more ductile, like I saw the curve has more displacement, they give more warning for people.
Yeah, actually, the displacement will increase than the limit of the code if the L over 250. So actually, it experience large displacement, and this causes failure, or at least will be inaccessible for yeah.
So domes design is kind of limited by the displacement more than the strength. Both.
Yeah, the serviceability limit state states that the displacement shouldn't increase more than L over 250. And the ultimate limit state says that no buckling in struts and no yielding or slacking in cable. So both limit states should be maintained in your design.
Thank you.
Yeah.
Other questions from the audience?
Yes, which software was used for simulating the dome actually? Which finite element software was used for this project?
Sorry?
Which software was used for this project? Software.
Yeah, actually a lot of projects connected together. For example, the nervous curves, I developed using MATLAB and developed the form and prepare a text file to be imported in ANSYS. ANSYS is responsible for performing the arc length method. It's a finite element commercial program, but it needs some programming to import and export the results and develop the feasible form and the optimized cross-section. So starting from MATLAB and transferring everything to ANSYS at the end.
What will define the failure criteria?
The failure here actually governed by three criteria. The first one, the displacement, if it is larger than the code limit L over the diameter over 250. So for this dome, the diameter was 100 meters. So if it is experienced displacement larger than 0.4 meter, we will assume it out of service. Okay, so for the second one, the stability, the buckling in the struts shouldn't increase that the limit in the Canadian code. And for cables, usually we need the cables to be always in the elastic range, not in the plastic range. So the yield limit is our maybe the critical stress for designing cable. It actually may go into the plastic range and is still on surface, but we don't prefer to do this. Okay, so the yield limit for cable is our critical stress. Does it answer your question? Thank you.
So, sorry, last question, go ahead.
So I was surprised to see that the positive dome performed worse than the flat one. So if you consider concrete, a shell will perform better than a flat slab, right?
Yeah, actually, it is not a flat. It's not totally flat. It is zero curvature. It is like a cylindrical shape.
Okay.
It is a straight line here moving over a straight line. So it is different than the flat roof. So the positive one actually more stiff and rigid than the flat one because of the arch effect. Yeah, you are right. But moving towards the zero curvature, it does different behavior because it's the stabilizing curve, which is a straight line, give more stability to the. Okay.
So, thank you very much. Today's seminar. Thank you all for attending. See you all next week.